Dahmann from the MITRE Corporation. She is a principal systems engineer with this organization. Has been there for a generation, let's say, and has a great deal of experience at a very high level of systems interoperability. So if you're working with in the defense industry, she's at the level of getting the different branches of military to talk to each other and work together. And they like to operate, the Navy likes to operate as a separate system, but they have to cooperate with other branches as well. So she has great stories to tell about complex systems and how to get people to think through what systems engineering looks like when you're at the system of systems level rather than at the product or self-contained system level. So with that as introduction, I'll turn it over to you. Okay.
First, I really appreciate the opportunity to be here. System assistance is one of my favorite topics. Anybody who knows just simply ask for more than having to talk about it. In fact, once you get involved with systems, you see them everywhere. Sort of like when you use your family, you ask people, you have lots of other people have it. Because very often when things go wrong, they'll go over there, they'll turn to me, and say, that's all I know, it's the system. By the end of this talk, you'll be also doing this. Just some background about myself that might help you, understand the perspective that I get from the problem. I was here said that I work for MITRE Corporation. MITRE is a special kind of company. It's called a federally funded research and development company. I went from Washington, D.C., so we never say that we get in FFRDC. And as this special organization, we work kind of as a technical arm to the government. And we have sort of special relationship with them to provide technical advice. We don't work for a private company. So that when we advise, say, on the specification situation fighter or for the new special information system, we're not also working for companies that we can compete with to be able to build those applications. We work, the company itself houses multiple of these FFRDCs. I work for defense, so I come from a defense perspective. I'll be giving you a defense example. I'll be working through, a number of defense examples as I go through. But the the company itself is an FFRDC for the Federal Aviation Administration. Air traffic management, air transportation, a big system of systems problem. We also do a lot of work for the intelligence community, as you can imagine, lots of systems of systems. The IRS, the Veterans Administration, they all have lots of complex systems that need to work together collectively to provide a set of services or a capability. And so I'll try to sort of talk some about those sets of things because being in the MITRE Systems Engineering Technical Center, which supports the whole corporation, we have a lot of work not only with the primary customer that I would have, but also with the other organizations. My day job from MITRE is I work for the Director of Systems Engineering for the Department of Defense. And defense takes systems engineering very seriously. There was a period back in the late 80s where the decision was the government didn't need to care about systems engineering because the companies would. They found that wasn't such a great idea because when the government didn't care about it, the companies said, why bother? So there's been a strong emphasis now. The department requires that we have a chief systems engineer for the whole department, but mandated by Congress. And every military service has a chief engineer, and every of the major systems defense builds must have a chief systems engineer. And they have the technical responsibility for the planning and development of the system. On the government side, then most of the systems being developed by industry. So it pervades the systems side of defense these days, of systems engineering being very critical. And one of the things that I've been doing in that office is looking at how we take what we see as the benefits of systems engineering for these systems. Now, they're essentially products. They're large, complex products, but they're products. And how do we take the advantages we see from a disciplined technical approach for instantiating these individual systems to stepping back and using those same kinds of techniques to address the kind of capabilities that we get from combining multiple systems to provide air defense, for example, or to provide a warfighting vehicle where the vehicle is developed by one engineering team, the radio another, the sensor another, the antenna another, and they have to be integrated into a complex system. But each of those systems have their own requirements and their own objectives, their own users, but together they need to work as a system to provide the capability. So the question that I've been dealing with is, how do you take what we do with systems engineering and adapt it to the particular circumstances that you have when you're dealing with these complex capabilities that are comprised of multiple independent system of systems? So with that, start with some definitions. Always good to make sure we're on the same sheet of music. So first off, what's a system? It's a set of elements that work together to create some integrated whole that provides a value to a user. Systems engineering, then, is the process, and it's an interdisciplinary process right from the start, of going from an idea, a need, a requirement, and the realization in a system. And the term successful meaning it's a realization that actually meets the objectives that got it started. So you've got elements together in a whole to provide value, and then a process for actually realizing that value as a systems engineering process. We do this all the time, whether we call it that or not. Then when we start to look at system of systems, we've really got a particular type of system that provides a value or a capability, but the particular thing about it is that it's comprised of multiple systems that are independent and useful in their own rights, independent of that capability. But the capability itself really depends on bringing all of those together to create the value or the capability up at the system of systems level. I often say that system of systems are made up of systems that have day jobs. I mean, they're being used for other purposes for other folks, but then they're also being brought together to create this broader capability. We see a lot of this in defense. You'll have an aircraft carrier that supports a variety of different missions. It has different users that support it. But if you want to bring it to bear in missile defense, it needs to do things that may not be the same as what it does for the Navy that brought it to the party to begin with. And so these are the kinds of things, we'll talk more about this, that make system of systems have a set of particular characteristics that as a systems engineer trying to realize these, you have a set of new constraints that really have an impact on the systems engineering process, which is here sort of blown out a little bit more. It's really planning, analyzing, organizing, and integrating the system of systems to meet that broader capability. In most cases, systems of systems are comprised of things that exist already, that are out doing their day jobs, and then I've got another thing that needs to be done, and the question is, let's just use those to do what I need to do. And the process is, how do I bring those together and actually achieve that capability? So not only are they useful and independent, but they usually exist. And they were developed and designed for their original purpose, which may be quite different from what I want to do with them when I bring them into a system of systems. And so the challenge of the systems engineer is how do I do that? Okay, so up until now I've been sputtering some examples along the way, but most people are thinking, okay, so what does she really mean? What are some examples of systems of systems? And these are here as illustrations, and I think one of the important things about system of systems is they underlie a lot of the major capabilities in society that we all depend upon. Very often these are not engineered from the top down, but we count on them working together effectively in order to provide some pretty fundamental functions in our society. And one of the things with system of systems is how can we as systems engineers take the things that we know to build the individual pieces we show up here and apply those to the collective. While I think you can tell by now this is something that I feel pretty strongly about, the International Council of Systems Engineering, which is the largest professional organization of systems engineers, has a new vision. It's called Vision 2025. Google it. It's nice, glossy. It's called World in Motion. And it really is putting forward the challenge to the systems engineering community of what do we as a discipline have to offer to really address these kinds of large societal problems, where the view is that we bring a perspective as an interdisciplinary discipline that can actually pull together these diverse pieces, different talents, different issues to create this whole. And throughout the vision, there are system of systems issues at each step along the way. And so I think this is really looking at a future role for systems engineering. Just not to say that we still don't need excellent engineers, systems engineers, to develop the pieces, but more and more of those pieces achieve their value not as pieces, but as part of these larger system of systems. So, for example, as you start up with energy, many of you have read the stories of massive power outages due to actions taken by different parts of the larger enterprise of energy of different companies with different procedures and systems with unintended effects, bad effects that create large dysfunctions based on small changes. One of the things that, back here. Get this button here. One of the things you'll see up here, this little corner, there's squirrels chewing on wires. And so say, so what is that doing with energy? Well, again, if you Google it, there was a whole series of articles in the New York Times summer before last about the number of fairly large power failures that are due to one squirrel chewing on one wire. And the interdependencies among these other systems lead to pretty large and catastrophic effects. Another characteristic of systems and interdependencies and unexpected behavior with changes in one part of the system, one of the constituent systems for the others. Water. Pat and I had some really interesting discussions this morning about water is really a large system of system. You have multiple elements. What you do upstream affects downstream. Different users look at the same resource and anticipate it as theirs, whereas in fact there are others who have similar objectives that may be conflicting and competing with theirs. And how do we as systems engineers not necessarily only design the reservoir, which is a really important thing from a civil engineering perspective, but look at the interdependencies among that so that you end up with water coming out of the spout when you turn it. Sir?
Where in these pictures is the political subsystem? Political
aspects of systems, just like economic, social, are in many cases profound. And one of the real challenges that we'll talk about as we go forward is that as systems engineers move into this domain, when we talk about interdisciplinary, it may be a challenge to get the aero and mechanical and the information systems engineers together, but here you're interdisciplinary. It's, your political analysts, your sociologists, the economists have a big impact on these systems and systems. A very important point and a big change for systems engineers who, with design thinking, we're trying to bring the user into it, but here the user is often a component of this larger enterprise as a system of systems. Air transportation, I kind of alluded to this earlier, the work that we do at MITRE. I was originally scheduled to give this talk back in September, and due to the air transportation system of systems, I flew to Philadelphia, spent the evening there, and flew back to Washington as opposed to coming here. So I think we've all experienced the air transportation system of systems in all sorts of ways. And then defense, which is where I come from. This is, I think, a place where it maybe first got a lot of focus, particularly here in the U.S., because typically our military missions, missile defense being a good one, really do require coordinated action among multiple systems that are multi-mission systems and are doing other sets of things. They're often built, fielded, and used without really engineering the overall end-to-end, we'll call it a kill chain or a mission thread, which drives how the users use the system, but doesn't always drive how we design the systems. We develop the requirements for that system, often using inputs from the larger context, but then we often put the larger context aside and then drill down and do trade-offs within that system's boundary. And the external kind of elements that would really impact whether that system got the user what it wanted, if it's not within that boundary, typically the engineers and managers of that system see it as not being their purview. An example of this is our military satellite communication systems. The way we develop these in defense, the satellites are the purview of one set of program managers, the downlinks another, and then the ground stations typically are developed by the people who are going to use the data. And we have some unfortunate examples of some exquisite satellite capability that has been launched and fielded. However, the ground stations that would use that capability were not developed and weren't deployed until after the healthy life of those satellites. And the senior leadership says, how can that happen? Well, it happens because there's no engineer responsible for the end-to-end system of systems. Engineers are working on the components, the systems, the constituents, as I would call them in system of systems, and doing an exquisite job in that piece of the problem. But the question then comes, how do I look at the larger problem as a system and ensure what I'm doing in those pieces, and I have all the pieces to actually get the capability, which is what the end user wants to begin with. And how do you do that in light of all the fielded capability I have that may constrain what my new system is, given the affordability of upgrading or building new systems, which makes the whole process much more complex. And for engineers that like to deal with just the technical aspects of it, it's seen as just a lot of noise that's keeping them from developing the system they know is optimum. But it's a systems of systems trade-off problem that we should be able to take our tools and step back and actually provide that, and maybe provide better insights into what the individual systems ought to be doing so we get more value from that system, given that we've engineered it understanding the context. So having recognized that in defense, I can tell you for sure we have not solved it. We're trying to understand it. We're trying to provide guidance to folks to figure out how to deal with it. But I think largely because it's not a systems engineering problem in the traditional sense, we've been working on how does the systems engineer operate within that context. And these are some of the resources that we've developed that if you're interested in the problem are probably worth looking at, and they're all available on the web. They're done for defense, but they have intended much broader audience. This is a guide to systems engineering of system of systems, which we developed back in 2009. And in COSI, when we did a review of the broader context of people, not defense, but otherwise, this was one of the top 5 references that deal with system of systems. And it uses a defense context, but really is not defense unique. In that, we have something here which we call the trapeze model. We identified by going out to people who are actually doing this. I thought of this with the design thinking. We immersed ourselves with them and said, when you're applying systems engineering, but you need to bring programs and products together that are developed by different folks under different circumstances, what are the issues that you encounter and how do you go about doing that? And things like the political and economic issues are all discussed in this guide. The guide is not so much of a guide like you expect of here's how to do it and here are the steps. It's more like a Lonely Planets guide. If you've been a systems engineer for a system and you're now going into a system of systems environment, like going to a foreign land, you'd like to know other people who've been there, what did they experience and what did they recommend? And so it's really written from that kind of perspective. We then actually took this and tried to unwind that trapeze model into a more implementer's view. And I realized, Pat, after our discussion this morning, there's supposed to be a bar across the top here that says environment that's poking into it all the way along. I think the clip art lost it. But, it really says that unlike a system, when you have requirements that you then explore, design, implement, and test, a system of systems, because it's out there already, doesn't fit that kind of a process. But in fact, what it is more of a wave-like process where you start out with some reason deciding that this set of systems, missile defense is a good example, something happens, the threat from North Korea to the U.S. said we cannot continue to take the risk of letting those systems work together as they will. We need to treat it as a system of systems. And you initiate a system of systems activity, backbone of system of systems analysis, to really understand what are the parts, how do they work together, what is the broader capability, how do I measure that, how well am I doing. All of that serves as the backplane for iteratively making changes in the systems or the way the systems interact or the infrastructure the systems use or adding systems to improve the end-to-end performance of that larger system-of-system capability. Not unlike changing the component of a system to improve the overall performance of the system, but that component of the system is probably not owned by the guy who needs the end-to-end capability, and they've got their own ideas of what you're going to do. So you deal with more social and political kinds of trades in order to be able to affect those sets of things. These kinds of things are then encoded in, for the DoD, when you do systems of systems, this is guidance as to how you ought to do this. It's in a guidebook that shows you these kinds of diagrams and what to do. And then it's in courses. And then finally, this is it's a little bit blurry. In the U.S. Defense, we have something called the Systems Engineering Research Center, which is a university-affiliated research center. It's a consortium of about 20 universities, all doing research in systems engineering in different ways. And one of the thrust areas in the systems engineering research is complex system of systems and enterprises. And so the idea is that there's a lot of unanswered questions about how to deal with a lot of these complexities. So this is a research thrust in the Systems Engineering Research Center to get systems engineers to really make investments intellectually and product-wise in tools to be able to address these kinds of problems. But defense isn't the only place that this is being looked at. I think it really started in defense, but I think the recognition and the breadth of interest in system of systems and these complex enterprise problems is in many ways, if you look at this left-hand corner here with the European Union, a huge topic of research for the European Commission. They've had research programs over the last 4 years in major infrastructure programs at 8 to 10 million euro to really invest in techniques and approaches, largely model-based approaches, to really looking at these complex system of systems to be able to address the end-to-end behavior and issues as a system, with close ties between universities, product developers, and industry to make sure that the needs of the industry and users were reflected in the intellectual endeavors of the university and the tool development by the others. And they just funded another whole slew of research programs in this area. In many ways, because the European Union is really a set of nations with their own infrastructure and their own companies and industrial base, they are more likely to want to find ways to build cooperative end-to-end capabilities across those pieces than I think in the U.S. we would just say, well, we'll compete it and let one of the primes build the whole thing. There, I think their whole culture and other things is much more to really look for a more heterogeneous approach with multiple partners. And so, overall, I think they see that this is critically important to them. And I've actually done some consulting with them, and I think they're pretty open about the fact that they think globally this is going to be a big problem, and this is their opportunity to really build up European industry in particular to be competitive globally, to be able to bring the kinds of engineering tools that we're going to need in order to provide greater assurance to these larger, more complex kinds of activities. I think the other things on here that are kind of noteworthy, INCOSI has a system of systems working group. I'm actually a co-chair with the BAE Systems person from the UK, where we've been looking at, and I'll touch on them a little later, pain points, what's hard about system of systems, how do we deal with this, the systems engineering body of knowledge. If you're not familiar with this is an online sort of global wiki with participants from across the world looking at bringing together what's understood about critical systems engineering topics. And we have a knowledge area on system of systems, which we're about to do a big revision on after the first one based on inputs from largely the INCOSI membership, but beyond that as well. And then IEEE has a large interest in this area. They've had yearly conferences. The next one's in San Antonio in May, all about system of systems. And the IEEE ISO 15288 standards for systems engineering, which is really the basic international standard. The one that's just finishing balloting now has an annex on systems of systems and how do you adapt the kinds of things we use for systems and use them in the context that we find ourselves in the constraints of systems of systems. So I think it's a topic that is sort of growing in interest across the systems engineering community. Again, I can reassure you there's plenty of opportunities for work. We're very often trying to really discover the problems and alternative ways for dealing with them. If you say system of systems to most folks, the first name that comes to mind is Mark Mayer. He's with Aerospace. His paper on architecting principles for system of systems, in the INCOSI sample, it was number one by far. It's really the best sort of articulation of key issues. And the definition I gave of system of systems earlier is the one we use in defense. Any paper on system of systems has sort of an obligatory paragraph that says there is no clear definition, settled definition of system of systems. But I think when you look across them, they all build on these Mark Mayer characteristics. And in my mind, it's this operational and managerial independence of the systems that is really the core of the activity. Often they're geographically distributed, though more and more we're seeing software systems that could all be virtualized in a stack and have a lot of the system of systems issues we've got as well. And then evolutionary development. When I go places and people say, "Oh yeah, I work on system of systems. We're developing one and we're going to deploy it." I realize they're probably talking about something different than I am, because mostly these are out there and they evolve based on changes made in the individual systems. And I think unattended, they actually could devolve based on the changes made in the system of systems. We have a couple of very critical defense capabilities that I probably can't talk much in detail about, but we designed them, we fielded them, we said we're done, and we came back 15 years later to find out that critical pieces of them have continued to develop, and there's some real fragile points in the end-to-end capability that we take for granted in terms of sort of critical defense functions. And that's caused for a joint system of systems engineer to be put into place to actually look at that and then attend to it over time. And I think the last one, and I'll talk more about this in the end, is this idea of emergent behavior. This is not unique to system of systems, but if you've got complex systems in their own right and you bring them together, the end-to-end behavior you'd like to be predictable. You're looking for emergent behavior. You want new behavior to come from pulling these together, but you'd like it to be the new behavior you want and not unanticipated emergent behavior. And that's really one of the real key issues for systems engineers working system of systems, is to figure out how do you identify the potential for this, how do you identify it when it's happening, and then how do you address it as you evolve the system of systems to provide the capability. System of systems vary in scale and scope. This both makes it very difficult to talk about sometimes, but really interesting to work on. These are examples that have actually come from some of the ongoing research projects. This one over on the very technical side is a project out of the Compass program out of Newcastle. Bang & Olufsen was the corporate partner. They have networked audio-visual devices, high quality. They recognize that people are buying other devices and wanting to plug them in. And their question was, how do you design that system of systems so when that happens, you retain the core qualities that the core system was to offer in light of those added systems that they don't control? And again, I think this is sort of another recognition of the commercial world that nobody controls the market anymore. Everybody's got pieces people are bringing together and system of systems and designs to be able to deal with that, becoming increasingly commercially important. This middle one came from the DANCE project out of the European Union. It's disaster response. And they had a couple of particular geographical areas, regions where the real question was, how do I coordinate police, ambulance services, private hospitals, and the like to provide effective disaster response in my particular area? Again, you're moving into more of a socio-technical kind of a problem, economic incentives of the various players. But again, you want to have a cogent capability at the other end. This last one is being done is a project being done under the Systems Engineering Research Center between Stevens Institute and Georgia Tech, and it's all about counterfeiting. We have a big problem in defense of counterfeit parts. And those counterfeit parts are a risk to our systems. And very often what the top-down bureaucracy in defense wants to do is say, well, I'll just forbid them. Or I'll tell people they have to report them, all of which they've done. But then the real question is, well, how is that going to actually do something to change the larger system of system enterprise ecosystem so that we don't get these counterfeit parts? Really interesting GAO report where they actually did a study where they put out on a e-business site procurement of parts. These were electronic chip parts, and they actually put out some that were parts that were never ever produced and weren't really part of the system, but they got bidders who would supply them to them. They also have done analysis of these counterfeit parts, and very often they're made of the refuse that we then export to other parts of the world, who then take it, shine it up, put more things on it, and send it back. That's all part of that larger system of systems enterprise that contributes to the end problem you're trying to solve, but you're not going to necessarily solve that problem unless you understand it in that larger counterfeiting enterprise system of system context. So this is an excursion to see how do you actually model that, represent it, and try to understand it to figure out where are your leverage points to have an impact on it, so that you can get the end state you want from the larger end-to-end capability. The interesting part, I think, for a lot of people is if I'm a system developer, and I'm the guy right up over here, what does this mean for me? And I think that one of the things Peter said, well, if it's a sort of you're building a standalone system. And I guess I think in defense, I'm not sure we have any of those anymore. And so what do you do when you're developing a system to understand where you fit and how you address this? This is another view of the system of systems evolution process from the DANCE project. You'll see our friendly V down here where the individual systems are going through updates, but they're actually the foundation for the larger system of systems. This is another one from the Software Engineering Institute about different architectures for bringing together multiple independent components to more effectively deal with the system of systems kinds of issues with more standard layered architectures when you're working kind of in the IT domain. And then this is a product which just came out last year. I work as part of an international group. TTCP is the Technical Cooperation Program of the English-speaking nations in defense. And it really looks at the systems engineering process and the systems development at each of these key review points, and really tries to identify, if you're a system developer and you're at those key review points, what should you be asking about the larger system of systems that your system is going to fit into in order to reduce the risk that you're making a decision about your system that will ultimately, when it's deployed, disable it from operating effectively in the environment that it's going to operate. And while we, I think, inherently believe that's an important part of systems engineering, more and more as these projects get complex, we try to focus on the inside and not think about the external impacts. But for defense systems, where it can take us a decade to develop these things, the world changes. And if you don't ask those questions along the way, you may have assumptions about things that are going to be there. The precision sensors that are going to support that precision weapon you're spending millions of dollars on. If the decision is to cancel that sensor program, probably want to know that, because it's going to make a difference as to whether or not your system is going to get the effects that you want it to have. This comes actually from the CBOC, and I won't go through it in any detail, but it really does say, in order to understand how to adapt the way we do systems engineering, it can be very important to understand the differences between systems engineering and system of systems engineering along a number of different contexts. I apologize, this is a bug that shows up pretty often when I use this slide. I will fix that for the final version. But management and oversight is usually seen as the biggest problem. Nobody is in charge. So the systems engineer is in a situation of having to bring these systems together, do the end-to-end kind of analysis, but then within the constraints of those systems, identify ways to make changes that could improve the overall system of systems activities. The operational focus is a big difference with most systems. We really try to get that end user clear focus in mind. With the system of systems, each of the constituents have that focus. The system of systems has a different focus. And so dealing with handling those multiple perspectives and looking for a solution that respects what the individual systems need to do, but also meets the system of systems needs, is the real challenge. Implementation, systems engineers believe they know the V model, how to go about doing this. With system of systems, each one of the systems may be at a different point of development. Their upgrade cycles may be different. We often see software on systems upgrades very frequently, whereas the platform, the hardware, doesn't change as often. Two systems, you're trying to work them together. We know we've got an interdependency. I can change on Monday. You can't change for another month. You tell me to wait. I say my system user needs it Monday. How do you test those? How do you validate that those things are going to work together? How do you avoid those kinds of surprises? And there's been a whole bunch, and it gets down into the test and evaluation area of how do you engineer and architect your systems so you mitigate those interdependencies so that you don't run those risks when systems change. And a whole set of those additional issues that you need to deal with as a systems engineer working across a system of systems. So why is it hard? Management and funding. You get a system. I'm building a new system. I need a precision feed from a sensor. Go to the sensor program and say, can you add that? And say, that's fine, but I haven't got resources for that. And I'm booked in terms of improvements in my system over the next 3 years. How do you handle those kinds of things? These independent, asynchronous developments. We really want everything to finish so we can test it and deploy it. Well, that may not be possible. How do you do that? And then multiple concurrent systems of systems. These things are not one big system, but there's lots of overlaps. And it's a recursive kind of process. How far up do you go? How do you look at those things across? Those are all issues you face when you address a system of systems, relatively unbounded kind of a problem. And that sort of brings us to these NCOSI pain points. When we formed the NCOSI System of Systems Committee, we said, well, if we're going to have a working group that draws people from a bunch of different places, let's understand what are the things we think are important to look at. And so we called them pain points. We did a survey. There's an NCOSI paper that lays this out in detail, but it was quite interesting because the biggest one that we saw across the board was this authority question, that when you don't have someone in charge who can arbitrate, who can flow down those requirements, how do you deal with that problem? Leadership. I don't know what you do in your program here, but I know in a number of the programs of systems engineering that I work with, this understanding that as a systems engineer, and increasingly as an engineer, you need not only the technical abilities to solve the problem, but the leadership capabilities to be able to articulate those problems to the users and the other folks working on the problem space, because the lack of awareness of critical technical problems can be, detrimental to the overall success of the endeavor. And so getting folks to be able to really have those leadership skills and the comfort and the expertise to do that. Capabilities and requirements in constituent systems. How do you do requirements in a system of systems? It's not the same. There are alternative ways to think about the larger capability, the gaps in that capability, and in a more open way look at alternative ways to make changes in order to meet those capability objectives. And then constituent systems who have been designed to do one thing, what are our technical approaches to allow them to adapt those while continuing to do what they do now? As well as a lot of the social and political issues about whose requirements are more important. If I have to make a trade, how do I resolve those issues? I think we touched on testing, validation. We added learning in there because, thinking you're going to develop, test, and deploy is just not a concept. So how do you learn from other areas, be able to make this work? SOS principles, how do you bring those together to really understand as a systems engineer what should I be thinking of as I deal with these things and really build that body of knowledge. And then finally, this autonomy, interdependence, and emergence, which from a technical viewpoint is kind of the most interesting problem I think we deal with in these system of systems. Basically, you're combining systems that have behaviors internally. I know in defense we often don't have good records of the current behaviors of systems, so when you bring them together, there's a risk that you get behaviors that you cannot predict. Even if you've got what you think are good models of those systems, we typically model the characteristics we care about, but there are other characteristics in those systems that can have impacts that we don't understand. The understanding those relationships, even in existing ones. So not only understanding the internal behavior, but the interdependencies and tracing them back. Often people decide to make a change in one part of the system and not realizing the downstream effects of that change. It can be a very big risk. And tools to deal with this level of complexity. There's a cyber-physical system of systems project from the European Union that had a state of the practice report that just came out last week. And they basically talk about the complexity of modeling these systems as being a large system of systems problem in its own right. And the DANCE project in particular from Europe talked about the need to have abstractions that are faithful to the details but are tractable in order to deal with these problems. So there are a lot of technical representation, analysis kinds of issues that underlie our ability as engineers to deal with what may seem like a very large socio-political problem, but it has really huge impacts on the complexity and tools we bring as engineers to deal with the problem in our discipline. Then, so this notion of complexity, this difficulty of predicting the results, the properties of a system when we know the parts. And that's often the case that we deal with here. And, ideally what you want are productive complex adaptive systems that they act independently, but then together they meet common constraints and goals. And our challenge is sort of trying to tame that complexity into that space in a way that I think there are some that are questioning whether that's within or beyond the bounds of engineering. But I think it's a challenge whether we think it's in the bounds of engineering or not. It's a challenge we societally have, and it's not clear if engineers and systems engineers can't bring to the table tools and approaches to deal with it. It's not clear who else will. So, just going back to some of the characteristics, what are the sources of complexity? Well, the systems themselves were designed with internal mindsets, design principles, and the like that may or may not fit together when you bring them into a common use. The stakeholder complexity. Individual stakeholders have their own points of view, their own needs, and may not have any awareness about the impacts that doing what they need has on others. The system development complexity, this notion of asynchronous development, that in many cases with a system being farther ahead may be just as bad as being further behind, because it's that mismatch and inability to adapt collectively. And then I think finally it gets to the non-technical aspects, these really complex organizational dynamics. The interdependent, independent operations of these systems where users are making decisions in their own space that have impacts across the board. And I think all of those are sources of complexity that we deal with as systems engineers when we approach this problem. So sort of in conclusion, I think there's a number of either challenges out there or opportunities for particularly those of you who are students in systems engineering, students in engineering-specific disciplines to really think about for your future career. The opportunities there are to take the tools, the things you're learning in the engineering discipline, stepping back and looking broadly as to how those can really be brought to bear, as I think engineering plays a stronger and stronger role in these larger societal concerns that I think impact people in new and different ways all the time.
Great. Thank you very much.
Questions?
Some questions.
Are you all ready to go out and tackle a system of systems problem?
If I could take you back to an earlier slide where you had in the bottom left-hand corner was the software architecture evolution.
Oh, yeah,
with the
Software Engineering Institute picture.
So that diagram on the far left, it's ad hoc architectures, and over on the right, there's looks like something where there's been a lot more, something else has happened.
Right, some order
So
or something.
In that sort of world, there was pressure on software development that forced us into developing layers and modules.
Right.
So the analogy in a system of systems world is there any external pressure that would bear on these systems that would create a like transformation of those systems into modular or layered approaches?
That trapeze model that I showed that had all the pieces that all iterated with everybody else, right in the center of that is the systems architecture. And I think, there are a lot of us who think that architecture, which we often describe as this net being thrown over these constituent systems and moving them in the direction that we want them to go, is the biggest engineering activity for the system of systems. And lots of discussion about the fact that you want to develop that architecture so that it accommodates the normal concerns of a system of systems, which is the individual systems making changes for their own purposes and buffering that from others. Wanting to unplug one system and plug another one in when something retires and something else is brought into bear or something comes in. So an architecture that's extensible. And a lot of attention now is being paid to what do those architectures look like. And what's interesting is it's very akin to, in defense now, we have a big push on modular open system architectures for tech insertion, because we realize we can't build a new system fast enough to meet the new need we found. But if we, in fact, have an open systems backplane to be able to plug in a new electronic attack system or another capability, we can then upgrade our long life platforms by bringing things in differently. So there's a lot of pressure and discussion in defense from that regard, but then also like the Bang & Olufsen example and others who want to bring in other players as you go along. So I think it's very much an analogous kind of situation up a level, with the individual components being things that are developed by a third-party provider, we would say, that you want to bring in. So,
yeah. Well, I think it's weird, the multiple leads there, and I was thinking about how you give us some examples of how you track things like interface. Obviously, you have to actively be tracking the interfaces between the systems and the systems. And then related to that is how does it work in practice when you see something that has a V diagram that's sort of out of phase with what you need, or a lifetime is expiring of a certain system people don't expect to maintain it further.
Right.
You know, how in practice do people deal with that? I see problems, but I don't know how you deal with it.
Well, there's one example that it's called digitally aided close air support that I know of, and the source of it was the end users said using all these verbal calls for air fire is fraught with all sorts of issues. Can't we digitize that? And in the very system-specific way of the U.S. Defense Department, each system said, sure, I can do that, and then started to do their own thing, which of course is not going to be very productive. And so the Joint Staff actually stepped in, the operators, and said, let's come together, let's see if we can come up with that kind of an exchange. And so they actually identified all the systems they would like to have. The sort of political part of it, some of them came forward and said, I'd really like to participate. Others said, I'll be ready for an upgrade in 5 years, so I'll do it then. This one has the advantage that you can always go back to voice. So you've got the fallback of the current, and the new one augments it. When you don't have that, it can be very difficult. You also end up with the issue where additional systems come in, and for whatever reason, their current design will not allow them to do it that way. So then the question comes, do you go back and revamp everybody else, and when you go forward to do this as you go along? And so they deal with it. It means that things take much longer. They do evolve. Things go off track at various times. And if you don't control all of it, and it's not important enough for somebody to step in with either a big slug of money or some other technical solution, it just tends to take much longer. In some situations in defense where there's recognized that these pieces fit together, they do put together like an integrated master schedule for all the systems, but then the system of system really looks at the kind of key sync points for each one, and then the key technical interface points. And I think the thing that's worked the best is if you can do that and then just only focus on those. And if the program makes all sorts of other changes and the like, but it doesn't affect the system of systems, the systems of systems engineering guys should keep their hands out, focus on just those things that are critical to the system of systems. And I think that's the way you get you manage some of that complexity, by understanding what those are, focusing on those, and then letting the rest of it go as it goes by. And those are the kinds of things. In some cases, on the military satellite communications area, they actually have things that are like configuration control exchanges. So they ask folks who are in the system of systems to share on a quarterly basis the things they're thinking about changing. And the systems may just assume it's not going to affect anybody else, but they expose that, and then if they identify the fact that, whoa, you're going to discontinue that data link, I use that data, and the other person, so who knew? Well, we know now, what are we going to do about it? And the new system may not be able to retain backward compatibility with that data link, but at least the receiver knows they need to do an upgrade if they're going to continue to operate. So it's that kind of providing visibility so actions can be taken in advance if possible, because otherwise what will happen is those changes get placed and you just find out in an exercise, hopefully, or in operations that the capability that you were counting on isn't there anymore.
Basically, once you make a system, you now have to watch every subsystem. I mean, the system that is part of your system must be watched by whoever's managing the system. So it really, it makes it much more difficult. As things randomly, seem randomly disappear, capability.
Right.
You got to be in there and deal with it.
Right.
So it's like not really you sort of own the whole mess then, not just an overview.
Right, and then the real question becomes, with configuration management, who owns what? Who's got the right to change what? And this one, high priority system, a system that I mentioned earlier, there's real struggles over that to figure out, if a system changes things, it hits these critical things. How do you get that visibility and get it early enough so that you can, in fact, deal with it otherwise? And I think that the fact that we're dealing with it now in defense, for example, whether we explicitly recognize it and try to deal with it. To say anything that I can do to start to identify those is making it better, and so we're kind of incrementally looking at ways to do that. Some nations have said, I'm going to put a whole new layer of system of systems management into my defense materiel system. And if you're a much smaller defense system, it may help. But even so, you've got multiple systems addressing multiple missions and areas. So it's really not a hierarchical process, which makes it a little tougher. Pat?
Actually, building off that point in the environmental bar. So in a lot of these things, if I think about administration, dependencies, and merging, there's a chicken and an egg paradox. And I'm just curious, in your perspective, if you've seen examples that have succeeded, because really you want to design positive feedbacks and incentives such that the system will steer itself to the right behavior.
Right.
But to do that, you have a systems integration problem where you have to actually be able to model the interactions and the dependencies, which often you don't even get the same people with two simple components able to model their dependencies. So
Yep. Yeah.
There are examples where there's been successes of trying to create the incentives and do that systems integration.
Well, I think the one where we've had the most success is probably missile defense. And you would think because it's such a high priority thing, it would be top down, but you still have the individual services using those systems for other things. And so, over time there have been things like who does the chief engineer of the system that's critical to missile defense report to? And having them report to different people changes their incentive structure and do that. So there have been examples like that dealing with the organizational and responsibility structures, that even though the system belongs to another service, the rating and performance appraisals of the chief engineer is really bounded by how well it supports the broader capability. And so there are a set of things like that folks have well, I say experimented. It's not really an experiment. They're trying in different places. And I think that one did have an effect on the missile defense side. And that's one where they really do, given the severity of the problem, have in fact modeled the end-to-end capability and try to track it. And I think that's the other thing that happens with defense is depending on how critical the capability is, the more people are willing to put the attention and the resources into ensuring that it operates properly. And it goes down as the priorities go down.
Other questions? Well, I'd like to thank our speaker. We have a small token souvenir.